Okay, so let's go ahead and draw on the forces. We've got force of gravity always pointing to the center of the earth, and the force normal is perpendicular to the surface. There's a force applied, and that's a new one for us. We don't usually see that, right? Excuse me. Did I miss any other forces? Oh, there's a coefficient of friction on the plane. So horizontal, the coefficient of friction, connect friction between. So there's friction, and friction actually retards the motion, right? So the force of friction is equal to mu Fn. So it looks like we are going to have to think about the y direction. And are they applying a force, or is this one just the force of friction? Oh, we have to pull the block up, and they want it to be constant speed. Okay, so that's super important.
When you did over there, you said the block would move down the ramp.
Yeah, I haven't read this one in a while, so I gotcha. All right, so it's constant speed. So let's redraw the free body diagram. Looks like this, like that. Oh, I see why you were trying to correct me. That makes sense. So this is the normal force, and this is the force applied. This is mg, and I'm missing a force then, because if they're going to pull it up and there is friction, I forgot friction, so that's the force of friction. And here's our force of friction. Remember, force of friction is going to be parallel to the surface, right? All right. So there's my free body diagram, and I'm not allowed to break out the component vectors on the free body diagram because we really want to know all the forces. So when you want to start breaking out x and y, you do the component vectors yourself over here. So there's mg, that's our weight. And today we learned that there's a cheat. This is theta. Mrs. Valletta, they didn't give us theta. Oh, they gave you a way to get theta. I'll show you in a second. And that this is the force in the x direction. So the force of weight in the x direction is equal to mg sine theta. And the force in the y direction, that's this one, is equal to mg cosine theta. And they're like, where's theta? Well, they didn't give us theta, but they gave us the length of the sides, right? And remember, this theta is equal to that theta right there. And so how are we going to do it? So, ka, to, a. All right, so it looks to me like we have the opposite side and the adjacent side. So the tangent of theta is equal to 3 divided by 4. So the antitangent is going to give us theta. So the antitangent of 0.75. Can someone do that? Oh, here, I got a calculator. All right. So I get a degrees of 36 point, oh, for simplicity, 87. Do you guys agree?
Yeah.
All right, do you see where you get theta? Okay, so theta is 36.86. All right, so I'm going to move off of this so I can write things out more. So we have everything now to start doing the sum of the forces, right? And we have to think about the y direction because we need to know about friction. They gave us mu as 0.3, and so we're going to calculate the force of friction first. All right, so I'm going to move over here. So in the sum of the forces in the y direction is equal to mass times acceleration in the y direction. And we know that's 0 because it's in contact with the surface. Yeah? So that's equal to 0. And how many forces do we have in the y direction? Well, it looks like we have force normal and the y component of gravity. The y component of the force of gravity. So if we do that, it's kind of hard to do that, but I'll redraw it over here. Force normal, and then we need the y component of the force of gravity, y. So we'll substitute that in. We said that the y component was mg cosine, and we just calculated theta to be 36.8, did we say 6? Yeah, 86 degrees, 87, my mistake. 87, and that's equal to 0, right? And do we know the mass? Oops, did I miss one? Oh yeah, I did, sorry. Minus force normal, sorry, the thing we're calculating. Minus force normal equals 0. All right, so we have to go in and substitute in our mass. We know our mass is 5 kilograms times 10 meters per second squared times the cosine of 36.87. And I'm just going to put F normal on the other side is equal to force normal. All right, so cosine of that, this mess, the cosine of that is 0.08, and this mess is 50 newtons. So 50 newtons times 0.8 equals 40 newtons. And so our F normal is 40 newtons. Somebody should be checking me. I'm doing this off the top of my head. So as long as you're following, I hope you guys are checking me just in case I make a mistake. All right, and then we need the sum of the forces in the x direction, which is equal to mass times acceleration in the x direction. And in this case, it's moving with constant velocity. I'm taping for people. It's moving with constant velocity, right? So we only have two forces. We have the component of gravity in the x direction, and we have the force of friction, and we have the force applied. So we've got 3 forces to deal with, don't we? Which is more than usual. So let's redraw the free body diagram in the x direction so that we don't get lost. We have the force applied, and what's retarding that motion is the force of friction, and then we also have the x component of the force of gravity. Everyone agree? Yay or nay? Okay, just want to make sure. And on our coordinate system here, ooh, I forgot a coordinate system. Okay, so we said uniform motion for the y direction, and in this case, in the x direction is going to be uniform motion too, thankfully. So what do you want? If we're pulling it up, let's call this the positive direction. Does that work for everyone? And this is the negative direction, so that we're keeping our coordinate system correct. And if we do that, then we're summing the forces up. This is the positive direction. So we have the force applied minus the force of friction minus the force of gravity in the x direction is equal to mass times acceleration in the x direction. And they told us we're trying to figure out how much because it's moving with constant speed. So that makes acceleration 0. So that's 0. So far, so good? All right, so let's start applying some things that we know. We need to figure out the force of friction. So remember, force of friction is equal to mu force normal. And they gave us mu. Mu is 0.3. So we put in 0.3. We calculated the normal force up here. That's times 40 newtons. Times 0.3. So our force of friction is 12 newtons. So far, so good? Okay, and our force in the x direction, well, our force of gravity in the x direction, when we broke out the component vectors, we said that's mg sine theta. And that's that thing that we're memorizing going up and down a ramp, that it's always mg sine theta. So this is mg sine theta. So we'll substitute in, okay. Well, what's our block? It's 5 kilograms times 10 meters per second squared times the sine of 36.87. All right, so 36.87 sine. So we'll call this mass 0.6. There's some decimals I'm ignoring, and this mass is 50 newtons, right? You know, we don't care about all those extra decimals. It's not significant. So 50 times 0.6 And we get that the force of gravity in the x direction is 30 newtons. Yay?
Yeah.
And what are we supposed to find? Well, we're supposed to find the force applied that will cause it to go at constant velocity. All right, so we're going to substitute in what we know, force applied minus the force of friction, well, that's 12 newtons, minus 30 newtons is equal to 0. So how much is the force applied? Yeah, equals 42 newtons. And because we know I stole this from another teacher and didn't write these questions, he did 41 because he likes 9.8 meters per second squared because he's old school. And I don't think we need to do it anymore. And let's just check. Is that the answer? Okay, 10B. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Indeed, that's the answer.